Hi YouTube, my name is BJ. I'm a Red Tech student of 2019, and I'm coming to you today to give you a quick, try and do a little bit of a demo about digital radiography and some things that are a little bit confusing sometimes. So I wanted to just kind of help you guys maybe visualize some of the things. We're going to be talking about the IR. We're going to be talking about photo timing cells, and then we're going to go a little bit deeper to the Del, and then deeper to the pixel, and then we'll try and finish off with some digital. So basically, when you're looking at and I'm kind of holding my phone at the same time, so I'm going to try and do this one-handed. When you're looking at also this is we'll follow along with Carlton Chapter 23, page 325, Digital Radiography. And when you're looking at, so this is kind of like this is going to be the IR. When you're looking at the IR, there are 3 layers to it. There's the top, technically there's 5 layers. There's the top protective layer, okay? And then there is the scintillator layer. Underneath that, you're going to have the, hang on just a second. Okay, you're going to have the scintillator layer, you're going to have the photodiode layer, and then you're going to have the thin flat panel transistor, or TFT, also called the thin film transistor. And we're going to talk about those 3 layers to begin with. So you after you go through the protective, on your IR, you're going to have 3 cells. Those cells will pick up light, and they will tell the machine how much exposure it's received, and then send back it's kind of like I think it's called a negative loop, where it says, am I exposed? Am I exposed? Exposed? Yes, I am. Okay, then it shuts off. For the AEC. So if you have a cell, if you have 3, you've got 3 cells, okay? So you've got 1, 2, 3. If you're doing an arm and you've got your arm over here, position is also needed. If you got your arm over here on cell number 2, and it's supposed to be, cell number 1, or it would be like this. If you're doing a lateral forearm, and if you're supposed to have that center cell activated, but not the 1 and 2, then what would happen is you would have wrong positioning. You would basically have an underexposure if the cell is not being covered. It would, because the IR would receive all that radiation, which there's nothing covering it. It's going to receive all that radiation, and it's going to say, "Hey, I'm done." So positioning is critical over those cells. Also, cell selection is critical. Underneath the top layer, which is the scintillator layer, scintillator is going to convert your X-rays into light photons. Okay? Top layer is going to convert your X-rays into light photons. X-ray comes down off the instant photon, useful photon comes down, strikes the scintillator layer. Scintillator means that it gives off light. It's going to convert that X-ray to light and go down to the second layer, which is going to be the photodiode layer. It's made of now we're going to do the more complicated one. This one is, we're doing the indirect digital radiography, and so with the TFT. So basically this one is going to be made out of a compound called cesium, let's see. Okay, top layer of the scintillator layer was made out of cesium iodide or gadolinium, either one of those. And this layer photodiode layer is going to be made out of an amorphous silicon. Okay. Now this one is going to convert the it's going to convert the light photons into an electric charge. All right. So it's going to, and then what it does is it goes down into another layer. See if I can get some space here. Goes down into another layer and to the Del. Del is just a shortened name for digital element. Don't know why they need all three, three letters for an acronym, but there you go. All right. So you got this Del, and this Del has, in this Del is really bad. This, like, you put your arm over this and you would get like, a black line basically. This is a terrible Del, but we're going to work with this. So so we have 3 rows of 4, 4 columns, 3 rows. In the Del, you're going to have 3 components. You're going to have a pixel or a pixel element, a switch, and a storage. The switch is going to tell it when to release its let's see, when to release its charge. All right, but we're not going to really talk about that. We're interested in digital radiography. Inside this pixel stands for the picture element. Okay, and basically, so you've got the photodiode that has transferred it's changed a photon that it received from the cylinder layer. It's brought down a negative charge on this pixel element, picture element, pixel. And actually it's not a negative charge, it is actually a 1. So what happens here is and it's not actually a 1, it's actually on. It tells the thing that it's on when it receives the negative charge. Okay, we'll put the 1 to the side. And on this Del, you have 1, 2, 3, 4. You've got 4. Well, actually, so you've got 12 pixels, right? So, and then if you have an adjoining Del, we'll actually kind of spread this apart here. Okay, so let's say that this is one Del with 4 pixels. We're going to say that this one over here is another Del. We're going to say that this one over here is another Del. Okay, the size of the pixels is in relation to the Del. It actually the larger the pixel compared to the Del, the better it's going to receive the charge, and the better spatial resolution that you're going to get, or better contrast is what you're going to get. Sharpness of an image is what I'm trying to say. So there's 4 here, okay, and each pixel is measured by the pixel pitch. Also has to do with it. It's measured from center of one pixel to the center of the other pixel. These ones are kind of bad because it's it's pretty far apart. You've got a large section here that's not really doing anything. So pixel pitch is also going to affect your your spatial resolution, and that'll come into the matrix later. So you've got 4 pixels here. Okay, that is going to give you So that's going to give you your pixel density, the number or fill factor. The fill factor describes pixels, your pixel density, like how many pixels are in a. Let me double check and make sure. Okay, where's my little cheat sheet? I'm going to grab my cheat sheet. All right, so yes, okay, so the TFT is a tiny little bump, like a Lego block. It's the del is. If the density is, it defines fill factor, and it's the how many pixels are in a del. Think of like peanut butter. Okay, you take some peanut butter and you spread it over one over part of the bread, right? Well, it's not really filled, but you spread the peanut butter over the whole bread and it's filled. So the pixel pitch is measured in microns. A micron, to give you an idea, is actually 0.001 millimeter. Now, the matrix size, or the size of the whole thing, matrix size is going to be a 2D array of pixels, and that all of this together. So you've got pixel, you've got the pixel density, you have the fill factor, okay. You have the matrix size, which is basically the 2D array of pixels, and then you have what's called a field of view. Basically, a field of view is our arm. It's the area that you're looking at. It is the, let's see, okay. So it's the scanned area. It can also be the displayed area. It can also be the area of interest. But basically, the field of view is, what are you looking at? If your arm is hitting these, is hitting some cells, and these ones are on, but these ones are off, and these ones are on with your arm, then it's going to kind of give you a geometric shape. Okay. And your matrix size is going to be basically the field, or the fill factor, or the pixel density, times the field of view, and that'll give your matrix size. Because your matrix size can't be your matrix size can't be larger than your field of view, because you're not going to be, you can't expose more, you can't expose more pixels than is only in the cassette. You can't see what's outside the cassette, or outside the the image receptor. So that's why a field of view is never going to be able to exceed the size of the matrix. But the matrix size can be slightly larger than a field of view, if that makes sense. Okay, so so you got your picture element. Photon comes down, hits it. It says, yes, I'm on. It changes that electron to basically a 1. And you get a bunch of 1s. So we'll place this over here. So basically you get a bunch of 1s and 0s. The ones that are on, they have a electron that hit them, where the arm is, where the arm is not. And the ones that didn't get hit, those ones are going to be off. We'll place this one over here. And that's how you get your 2D matrix. Is they're not considering the difference between a pixel and a digital readout. The matrix is both the density fill factor of all the pixels, right? And it is described as it's a two-dimensional array of pixels, but it's also a two x and y. It's an x and y dimension of a picture. Okay. The other thing, last thing that I'm gonna kind of go over is that when you turn, actually I don't know if I can do this correctly. That's not, but let's say that these were layered, okay, such as like a CT. Well, when you do that, then you're actually creating a voxel, because now the two overlapping squares, they create a field, a cube, a three-dimensional value that is now your voxel. Okay, so I hope I've explained everything. Remember, the Del has a switch, a storage, and a pixel. Pixel only, all it means is a picture element. Del means digital element. Dels have several. Dels can have several pixels in them. The pitch is between the centers of two pixels. Okay, and the matrix size is defined by the fill factor plus or times the field of view. So it could be like this, or it could be, 4 times the size. What is your field of view? How many pixels are in it? How many of those, how many of those are active in the field of view? I hope that was a good demonstration, and hopefully, you guys can pick up on this a lot faster than I did. And good luck to you in the future. Thanks.